Hello, everyone, and welcome to today's webinar, Myeloid Lineage Abnormalities, a journey into the world of myeloid diseases with cutting-edge flow cytometry technology. I'm Cassie Soltman of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Beckman Coulter Life Sciences. To learn more, visit www.beckman.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Submit. Also, if you experience any technical issues, you can utilize this Q&A box and we will assist you directly. I'd like to now welcome our speaker for today's webinar, part of a three-part series, Cara Shirai, Assistant Professor, Pathology and Immunology, and also joining is Antoine Pacheco, Platform Manager of Clinical Flow Cytometry. Cara, you may now begin your presentation.
Hello, everyone. Thank you for joining us today. My name is Cara Shirai, and I'm an assistant professor in pathology and immunology at Washington University in St. Louis, Missouri. I'm speaking about flow cytometric analysis of myeloid lineage cells for leukemia and lymphoma assessment. Here is my disclosure statement. I have three objectives with this presentation. First, I will describe myeloid lineage cells and the characteristics of myeloid neoplasia. Second, I will show the utility of flow cytometry in characterizing myeloid malignancies. Finally, I will demonstrate how the FDA-cleared Beckman Coulter ClearLab 10-color system, and specifically the myeloid tubes M1 and M2, work along with the Beckman Coulter Kaluza analysis software to perform efficient myeloid clinical flow cytometry assessments for patients being evaluated for leukemia and lymphoma. First, I would like to introduce myself and my laboratory. I'm an Associate Medical Director of the Clinical Flow Cytometry Laboratory at Barnes-Jewish Hospital in St. Louis, Missouri. Our flow cytometry lab performs a variety of clinical testing, including leukemia, lymphoma, immune competence and deficiency, enumeration of CD34 stem cells for hematopoietic stem cell transplant, and others. We serve 13 hospitals within our system and 5 ambulatory Siteman Cancer Center locations. We perform almost 9,000 leukemia lymphoma tests and over 11,000 immune tests annually. The ClearLab 10-color system has been the backbone of leukemia lymphoma assessment in our laboratory since October 2020. We use this system in conjunction with LDT reflex and other panels for complete characterization of hematologic malignancies. We currently have Beckman Coulter Navios flow cytometers. However, we are in the process of validating our new DxFLEXs. Kaluza analysis software is used by our flow technologists, as well as pathology residents, fellows, and hematopathologists for analysis. Hematopoiesis is the process by which blood cells of all types are formed from multipotent hematopoietic stem cells. The terms lymphopoiesis and myelopoiesis refer to this process within the specific lineages of blood cells, lymphoid and myeloid, respectively. The previous two sessions of this 3-webinar series covered the B lymphoid and T lymphoid cell types, which are involved in the adaptive immune system, and cancers that arise from them. Cells of the myeloid lineages are more diverse in both nature and function. They are comprised of monocytes and macrophage, all types of granulocytes, megakaryocytes, and erythroid cells. Cells of both monocytic and macrophage and the granulocytic lineages are involved in the innate immune response. Megakaryocytes are the precursor cells that generate platelets for coagulation and hemostasis, while the primary role of the erythroid lineage cells is to transport oxygen throughout the body. Myeloid neoplasia refers to cancer of the myeloid lineage cells. These arise from cancer-causing genetic alterations such as mutations or chromosomal rearrangements that occur in the myeloid stem and progenitor cells. Myeloid neoplasia includes a diverse range of diseases, clinical presentations, and prognoses that depend on the nature of the tumor cell type. For example, diseases can be acute or chronic, involve mature or immature cells, and involve cells of specific lineages. Classification of myeloid neoplasia is done by cell and tissue morphology assessment, immunophenotyping by flow cytometry, immunohistochemistry, and/or cytochemistry. These will establish lineage and degree of maturation, as well as degree of cellular dysplasia and/or abnormality. This is used in combination with cytogenetic and molecular genetic studies for final classification. Myeloid neoplasms can be classified into basic categories as listed here. The disease categories highlighted in red are more common, so you're more likely to run across these in clinical flow cytometry work. Myeloproliferative neoplasms encompasses diseases like chronic myeloid leukemia, polycythemia vera, essential thrombocythemia, and primary myelofibrosis. Myelodysplastic neoplasms, previously called myelodysplastic syndromes or MDS, are the most common myeloid malignancy, typically affecting elderly patients and having a propensity for transformation to acute myeloid leukemia. Myelodysplastic myeloproliferative neoplasm have aspects of both myelodysplasia and myeloproliferation. CMML is an example. Acute myeloid leukemia and secondary myeloid neoplasms can also be frequently seen, especially if you have a large cancer center like we do. Immunophenotyping of myeloid antigen expression patterns via flow cytometry is beneficial in the diagnosis of hematologic malignancies. Cell antigen expression patterns during normal myeloid lineage differentiation have been well described. By knowing what normal is, we can readily identify abnormal cell antigen expression patterns. The heat maps on the right side of this screen display antigen expression levels at different stages of cell maturation for granulocytes, monocytes, and erythroid lineages. The darker the color, the more antigen expression. These informative schematics can be helpful to refer to during interpretation of leukemia lymphoma flow cytometry analysis. Flow cytometry is an ideal method to assess both normal and abnormal cell antigen expression patterns. Current FDA-cleared flow cytometers have up to 10 to 13 detectors to allow for 10 to 13 different cell antigens to be measured simultaneously in a tube. In addition, there are many combinations of analyte-specific reagents, or ASRs, with many antibody clones approved by the Human Leukocyte Differentiation Antigen Workshops. An FDA-cleared panel incorporating ASRs is available in the 10-color ClearLab system. There are important considerations when designing a panel for leukemia lymphoma flow cytometry analysis. In 2006, a group of experts met in Bethesda, Maryland to provide the clinical flow cytometry field with guidelines for medical testing indications, the cell antigens that should be assessed, and the important components to include in a pathologist report. The recommended flow cytometry panel design should address the medical indication for testing, account for all major cell populations that are expected within the specimen, and be comprehensive enough to identify all relevant major categories of hematopoietic neoplasia for the medical indication. Now, this is not to say that all things must be measured on all specimens. In fact, that is not necessarily recommended or always possible due to specific specimen limitations. But the initial assessment should be comprehensive enough to screen for all major disease types. Then additional reflex flow panels may be added on for complete identification, subclassification, prognostication, and nowadays to assess for therapeutic options. This table displays the recommended antigens to be used in an initial evaluation, which is still relevant and appropriate today. All these antigens are included in the ClearLab 10-color system of 4 tubes, B, T, M1, and M2. The M1 and M2 tubes contain all the antigens indicated for assessment of myelomonocytic cells. Here is the schematic of the 4 tubes included in the ClearLab 10-color system. The M1 and M2 tubes contain the pertinent cell antigens for identification of myeloid cell lineage and maturation stage. Note, there are overlapping antibodies that are duplicates of cell antigens, and sometimes fluorophore as well within the ClearLab panel design. Overlapping antibodies are important in multi-tube panel design for correlation of cell populations across tubes. The M1 and M2 tubes share 4 of the same antibodies: CD13, CD34, HLA-DR, and CD45. In addition to key duplicate antibodies across tubes, the ClearLab 10-color system has a predefined color scheme for gated populations in the clues analysis software that is maintained across all tubes. The consistency of colors of gated populations across all panels is a helpful interpretation approach that can assist in recognizing normal and identifying abnormal. In fact, we adapted our other leukemia lymphoma analysis templates to follow the ClearLab color scheme. Shown here is a bivariate plot of CD45 detection on the x-axis and the side scatter on the y-axis. 4 basic gates can be applied to hematopoietic cell populations. Lymphocytes are CD45 bright, have low side scatter, and are colored red in all 4 tubes, although CD19 gated events in the B cell tube are orange and CD3 gated events in the T cell tube are light blue. Monocytes are CD45 bright, have moderate side scatter, and are shown in green in all tubes. Granulocytes are CD45 moderate, have high side scatter, and are blue in all tubes. Finally, the CD45 dim low side scatter gated populations are colored in purple in all tubes. Keep these colors in mind as we will look at example flow cytometry plots or scattergrams using the ClearLab system later in this presentation. As I mentioned earlier, myeloid antigen expression patterns have been explored, and there are a variety of nice schematics in the literature to help in your interpretation. This image shows neutrophil maturation on the x-axis and antigen density or expression on the y-axis. Note the helpful cell images above the graph that show the stage of myeloid cell maturation. Immature myeloid cells express CD34, HLA-DR, and CD117, but cells lose expression of all these antigens as they mature. Mature myeloid antigen expression occurs later in myeloid maturation, and antigens CD15, CD16, and CD11b do not appear until the myelocyte or metamyelocyte stage. CD13, CD33, and CD45 are expressed all throughout myeloid maturation, although the level of expression of these antigens can vary. Both normal and abnormal myeloid blasts express CD34, CD117, and HLA-DR. Shown here is a normal patient bone marrow pattern in the M1 tube for CD45, CD34, CD117, and HLA-DR, all displayed on the x-axis with side scatter displayed on the y-axis. The normal patient has a small myeloid stem and progenitor cell population that is CD45 dim low side scatter and positive for all three antigens. This population is purple in all the plots. This is an acute myeloid leukemia where blasts express CD34, HLA-DR, and CD117. AML blasts do not always express antigens similar to normal myeloid blasts. In fact, changes in antigen expression patterns from normal to abnormal is one way we identify aberrancy by immunophenotype. Identifying aberrant patterns of myeloid antigen expression has some fundamental principles. It is essential to know what normal looks like in your flow cytometry panel so that you can recognize abnormal. The spectrum of normal you learned should include things like post-chemotherapy normal or post-hematopoietic stem cell transplant normal, and any other conditions that you may be reviewing as part of your routine practice, as these could alter cell populations or antigen expression patterns. High-quality data is also essential for identifying normal, as artifacts of bad processes or poor gating analysis can complicate or even compromise your interpretation. Finally, I recommend following WHO and ICC guidelines for incorporation of flow cytometry findings into any final diagnosis. Characteristics of malignant cells, or so-called hallmarks of neoplasia, include cross-lineage antigen expression, which refers to the gain of antigens of other lineages or antigens that are not normally expressed by the cells. For example, a B-cell antigen expressed by a myeloid cell. Abnormally increased or decreased antigen expression level relative to the normal. This can include loss. Examples of this include increased or brighter CD34 expression than normal on a myeloid blast, or complete loss of CD13 expression on a monocyte. Asynchronous expression of antigens for stage of maturation. For example, mature and immature antigens are co-expressed. Finally, abnormal homogeneous expression patterns whenever heterogeneity is the normal. Myeloid leukemias often express antigens of other cell lineages. CD2, CD5, CD7, CD19, and CD56 are common, with CD7 being the most common. Two of these cross-lineage antigens have been included in the M1 and M2 ClearLab tubes. CD7 is in the T cell tube, but also the M1. CD19 is in the B cell tube, but also in the M2. Expression of T cell antigens on myeloid leukemias is observed so frequently in our patients that we use the T cell tube in conjunction with the M1 and M2 tubes to evaluate returning patients with a history of myeloid neoplasm. Here is an example of cross-lineage antigen expression of an AML with blasts expressing strong CD7. Normal is included in the graph above for reference. Myeloid blasts can abnormally express antigens found only on mature cells, such as CD15, CD16, and CD11b, that are expressed later in granulocytic maturation. The M1 tube has both CD11b and CD16, while the M2 tube has CD15. In this example, CD34 blasts are shown to have heterogeneous and partial positive expression of the mature cell antigen CD11b. Since myeloid blasts often express antigens abnormally, it is important to appropriately identify normal cells in the CD45 dim low-side scatter or blast region of flow cytometry plots. Many things may be present in the CD45 dim low-side scatter region that are not leukemic blasts. These populations can be atypically expanded and even express myeloid antigens. The antibodies included in the M1 and M2 tubes can assist in discriminating most of these populations. Cell populations in the blast region that are not blasts include hematogones, which are B-cell precursors, basophils, which express some myeloid antigens and can be expanded in certain conditions, plasmacytoid dendritic cells, plasma cells, both benign and malignant, erythroid lineage precursors, and other non-malignant myelomonocytic stem and progenitor cells. Now, I would like to share a few patient examples with you. Case number 1 involves a 27-year-old female who presented with gum swelling and bleeding that was non-responsive to dental intervention. She also had a petechial rash on her anterior chest and lymphadenopathy of cervical, submandibular, and axillary regions. A CBC was performed as part of her evaluation, and it revealed anemia, thrombocytopenia, and leukocytosis with circulating blasts. She was referred to BJH Hospital with concern for acute leukemia. A bone marrow biopsy was performed, and the bone marrow aspirate was used to perform flow cytometry analysis. For reference, the top row of graphs shows a normal patient bone marrow flow cytometry with the M1 tube. The row below is case number 1 patient's flow cytometry. Note that the patient has an expanded region of 57% of total cells that are monocytes, highlighted in green, on the CD45 by side scatter plot. Display of monocyte-gated events on a graph with CD14 on the x-axis and CD64 on the y-axis for a normal patient show a small CD14-64 co-positive population that is consistent with monocytes. The patient's monocyte-gated cells express brighter CD64 and show a homogeneously dim to negative CD14 expression consistent with abnormal monocytic precursors. These monoblasts are also negative for CD13, showing antigen loss relative to normal monocytes, and are positive for HLA-DR, as shown in the third and fourth columns of graphs, respectively. Note, there are a few residual normal mature monocytes in the background of the acute leukemia. They are CD64 and 14 co-positive and also express CD13. HLA-DR and CD64 expression are often retained in monocytic AML, but CD14 is frequently lost or partially expressed. Now, we are looking at graphs from the M2 tube analysis. For reference, top row of graphs is a normal patient flow cytometry with the M2 tube. Monocytes have moderate CD38 expression, but this patient's leukemia cells are expressing CD38 brighter. CD123 is often expressed in monocytic AML, as is CD56, which is shown here from the T-cell tube. Also using the T-cell tube, we can examine CD4 expression. CD4 is dimly expressed in normal monocytic populations and is often retained in monocytic AML, as shown here, albeit a little bit brighter in expression. At our institution, we routinely perform additional assessments to ensure appropriate lineage classification of new acute leukemia cases. Expression of myeloperoxidase, which indicates myeloid lineage, can be assessed on leukemia cells by flow cytometry, immunohistochemistry, or cytochemical stain. Cytoplasmic expression of lymphoid markers can identify early lymphoid lineage commitment by leukemia cells. We perform cytoplasmic staining of CD3, CD79A, CD22, and TDT. TDT expression is often assessed on acute leukemia reflex panels as it can indicate immaturity of neoplastic cells. However, TDT can be positive in AML, so expression of TDT by itself does not indicate lymphoid lineage. Occasionally, other lineage-specific antigens may be necessary for complete classification of an acute leukemia. CD41 and CD61 can be used to indicate megakaryocytic lineage, and erythroid lineage can be indicated by expression of CD71 and CD235A. The final diagnosis for this patient was acute myeloid leukemia with KMT2A rearrangement. This is a genetically defined entity. However, the morphology and immunophenotypic findings classified this as monoblastic. Case number 2 is a 65-year-old male with a medical history of diffuse large B-cell lymphoma, currently status post-treatment and autologous stem cell transplant 8 years prior. The patient was recently diagnosed with therapy-related myelodysplastic neoplasm, or MDS, with a complex karyotype. And he is currently undergoing treatment with decitabine. A bone marrow biopsy was performed for disease monitoring, and the bone marrow aspirate was used for flow cytometry analysis. For this case, the Clear Lab M1 tube is helpful for characterizing the patient's disease. Again, I'm showing the normal bone marrow antigen expression patterns for reference in the top row. In the first graph of CD45 by side scatter, there are 2 distinct findings that are common in MDS. First, the mature granulocytes have notable reduced side scatter when compared to normal. This is because the neutrophils are hypogranular, which is a frequent observation in MDS. In addition, the CD45 dim low side scatter gate is increased at 12% of total cells. This is a discrete population that expresses CD34 as shown in the second graph, indicating the patient has increased blasts. The blast population also has a relative increase in the level of CD34 expression when compared to normal myeloid stem and progenitor cells. Recall that over or underexpression of antigens is characteristic finding in malignancy. Dysplasia or abnormal differentiation of granulocytes can also be observed in this patient's flow cytometry when reviewing mature neutrophil antigens, CD13, CD16, and CD11b. In the third column of graphs, CD13 is on the x-axis and CD16 is on the y-axis. A normal neutrophil maturation pattern is shown in the top graph, which resembles a Nike swoop turned on its side. The MDS patient scattergram notably lacks granulocytes in these various stages of maturation. A similar finding is seen when CD16 is displayed on the x-axis and CD11b is on the y-axis. In a normal bone marrow shown in the top graph, a sideways L shape is formed by maturing granulocytes. The spectrum of normal maturation is lacking in our patient's bone marrow sample. While flow cytometry findings are not diagnostic of MDS, they can be contributory by identifying abnormal patterns in cell differentiation. There are a number of proposed scoring systems to assist in the evaluation of MDS by flow cytometry. Features and cell populations to assess include myeloid stem and progenitor cell frequency and associated antigenic abnormalities, as well as their relative ratio to B lymphoid progenitor cells. Also assessed are abnormal antigen expression patterns and characteristics of differentiation of maturing myeloid lineage cells, granulocytic, monocytic, and erythroid. For more on MDS flow cytometry, I recommend a very nice recent review article published in Cytometry B in 2022, shown here. The final diagnosis rendered for this patient presented in case 2 is myelodysplastic neoplasm with increased blast, or MDS IV2, post-cytotoxic therapy. Our third and final case is a 48-year-old female with a history of CML, BCR ABL1 gene rearrangement positive who presented at a routine monitoring appointment with hyperleukocytosis, the white count of 325, and significant anemia. These findings included a differential of TKI therapy, non-adherence, accelerated phase of CML disease, or transformation. Therefore, a bone marrow biopsy was performed and the bone marrow aspirate was used in flow cytometry analysis. Myeloproliferative neoplasms can have more subtle findings in flow cytometry testing when compared to other myeloid neoplasms like MDS or AML. When viewing the CD45 by side scatter plot of this patient's bone marrow compared to normal, we note an increase in granulocytes relative to other cell lineages, which is a common finding in CML. We also note that there is an expanded CD45 dim low side scatter gated population that is 10% of total cells. However, recall from our earlier discussion that not everything in this region is a malignant blast population. And indeed, this population is predominantly negative for CD34, CD117, and HLA-DR. Basophilia is a common finding in CML, and basophils are CD45 dimmer and have low side scatter. Careful evaluation of antigen expression and correlation with morphology is required to avoid overcalling. The immunophenotype of basophils is listed here. They are CD123 positive, HLA-DR negative, CD34 negative, CD117 negative, CD33 positive, CD13 positive, CD38 positive, and CD11b positive. The CD45 dim loci scatter population of interest shares this antigen profile. Note that there is a small population of basophils in the normal patient bone marrow sample. Their CD123 expression is quite bright, while our CML patients' basophils are dimmer for CD123 expression. Reduced CD123 expression has been observed in CML. An additional common finding in CML was present in the ClearLab T-cell tube analysis of this patient, which shows aberrant CD56 expression on granulocytes. The final diagnosis of this patient is more descriptive, which is common in CML. Markedly hypercellular bone marrow with myeloid predominance, moderate bone marrow fibrosis, and no increase in blasts. With that, I would like to conclude my presentation today by summarizing the main topics we reviewed. Myeloid neoplasms encompass cancer cells from the granulocytic, monocytic, erythroid, and megakaryocytic lineages. Myeloid cell antigen expression patterns can be readily detected by flow cytometry, and this includes both normal and abnormal. Abnormal myeloid lineage cells can be easily assessed for leukemia lymphoma analysis using Beckman Coulter FDA-cleared ClearLab 10-color system, BLUSA analysis software, and accompanying templates and tools. Thank you.
Greetings and a hearty welcome from our Customer Experience Center in Vienna. I'm Antoine Pacheco, the Global Platform Manager for Clinical Flow Cytometry. I'm currently in our state-of-the-art flow cytometry lab, which spans 233 square meters and is dedicated to live events, where customers can explore our workflow solutions in gene therapy, extracellular vesicles, and clinical applications. Depending on the lab size, assay menus, and objectives, we offer solutions to enhance efficiency for clinical flow cytometry, with application-specific technological advancements. Here, you can see our Aqueous CL load and go flow cytometer designed for automated lymphocyte subsets and stem cell analysis. Next, we have the CellMec SPS instrument, which fully automates complex sample preparation procedures, including RBC lysing, cell staining, and washing. And now, let's introduce the star of today's session, the DxFLEX flow cytometer. It's finally arriving in the United States, completing our global presence. One of the first things you'll notice is its compact design, which saves valuable lab space and ensures easy of use even in smaller labs. With a weight of 36 kilograms, it's easy relocatable. Let's take a closer look at the instrument. So the DxFLEX operates without a large noisy compressor card. As you can see, there is nothing in the bottom, thanks to the built-in peristaltic pump that efficiently delivers cells into the system. No need to check a separate compressor or switch additional devices on or off. Just press a button and the system will start. The sheaths and waste tanks on the side are easily replaceable. The DxFLEX allows you to add more columns to your panels without adding complexity. It simplifies high complexity testing. And I will demonstrate how it works now. Equipped with 3 lasers and up to 13 colors, it is CE marked for in vitro diagnostic use. In the US, the DxFLEX flow cytometer is intended for 10-color immunophenotyping with the ClearLab 10C reagent system. Fluorescence channels FL11, 12, and 13, and all other uses are for research use only. Now let's have a look inside the system. So if I open here the cover, the lasers are in this box, the 3 lasers, the red, blue, and violet laser. And you see here for each laser, we have the optics here with the famous avalanche photodiode detectors. So each laser has its own detection module with small optical filters and avalanche photodiodes. You can see here on the right side of the system, this is the autoloader. It's the famous known carousel from Beckman Coulter. In the carousel, a 32 position tube, you have a triple identification with barcodes. So inside the system, you have a barcode reader, and you can read the carousel number, the position of the tube in the carousel, plus eventually the barcode on the tube. And as you can see here, we have here a single tube vortexing. So it's a real vortex who takes each single tube and vortex it individually. As you know, it's really important for critical applications to maintain the homogeneity of the sample. In the B-cell webinar, we demonstrated how fast the startup of the DxFLEX is and how easy the QC and standardization process are. In the T-cell webinar, we focus on the digital data transmission. And today, we'll highlight more unique features of the DxFLEX, and we'll create an experiment with a panel of multiple tubes using the M1 and M2 tubes from the ClearLab 10C system. Before starting with ClearLab 10C myeloid tubes, I would like to demonstrate the power of the avalanche photodiodes. How the DxFLEX simplifies flow cytometry by gain-independent compensation. The gains of the APD detectors used in the DxFLEX flow cytometer can be calibrated for a linear response, leading to the predictability of the signal. So what I have done, I have prepared an 8-color sample. And I will show you now what the power of the DxFLEX. So let's start first by this tube 8 color. So I will select the carousel first, then select the tube with in position 1, put it in position 1, and start the acquisition by selecting the run. Okay. Can close this window here, and let's see. So the protocol is already set up. It's an 8-color panel. The system will start the acquisition here. You will see the different populations. So acquisition is starting. You see here lymphocytes, monocytes, neutrophils, and you see some graphics for compensations here. Okay. So the beauty of that, of the avalanche photodiodes, let me first open the compensation window. You see here the values actually of the compensations who have been set. Now, if I click on the graphic, this one is the APC Alexa 700 versus APC. I click on the gain settings, and if I change the compensation here, the gains, sorry, here, you see that the system will recorrect automatically the compensation values based on the new gains. I can do it multiple times. So now, the good feature of the system is if you need to adjust the gains for any reason, you can do it easily because the system is able to readjust the compensations based on the intensity you have adjusted. So this is really the power of the avalanche photodiodes. So let's stop here. So remember, for ClearLab 10C application, specimen by specimen compensation settings is not recommended. Once the system is standardized and verified, any deviation from expected pattern should be investigated to determine the appropriate remediation. This is really a very nice, unique feature. So let's now go back to the ClearLab 10C myeloid tubes. Go now for an experiment with multiple tubes. I will show you with the M1 and M2 tubes, the two myeloid tubes. I will run the ClearLab control cells, the abnormal one, with both tubes, the myeloid 1 and myeloid 2. So I have already prepared both tubes based on the instruction for use. So I have the abnormal M1 and M2. I will put it in the carousel in position 1 and 2. I have already prepared here a template, an experiment, which is called the myeloid tube, where you can see here, I have two tubes in this experiment. And if you look for the report, I integrate in one unique report both results from the tube M1 and M2. So I have the graphics of all the single column, all the columns from the antibodies, plus a statistic box where I combine the lymphocytes from the tube 1, tube 2, and also the monocytes and the neutrophils. So let's see now how it shows. So I select the carousel number 1. Here I select my panel, all the tubes, so both tubes. I put them in position 1 and 2. Press OK. I'm ready. So now just need to press initialize. Takes 2 minutes and auto record. So the system will acquire first the tube M1 from these abnormal control cells. The same strategy from the templates available in the Beckman Coulter website, where you see here forward scatter doublets discrimination with the area and the height of the peak. You have also the forward scatter, side scatter to eliminate debris. And then you have the cartography of the cells again with lymphocytes, monocytes, neutrophils, plus the immature cells here with a dim CD45 expression. I will put more cells in their position. So you can see here we have normally abnormal cells. So if we check here the CD34, as you can see, we have abnormal populations. Okay, and at the end, so I will not acquire too many cells. It's not needed right now, just to show a combined report for two tubes. I will stop it to go to the next tube. Same getting strategy. Again, you see here the different white blood cells populations. And again, normally, if we look for the 117, we see an abnormal population here. Same thing for the CD34. So we see these abnormal cells. So again, I will not acquire too much cells at the end. It's not needed, but if I press stop now, now if you go to the report, the system, you will see, will combine. On the top here, I put the graphics from the tube 1. On the second line, from the tube 2, where you see FITC, PECD, and PC5.5 with markers depending on the tube. Same thing for the other columns here, where you see the different markers. And here you see the statistics combined. So 31% on the lymphocytes from the tube M1, 32% for the tube M2. And same thing for the monocytes, 13%, 15%, and 47% and 50%. So you see here, it's easy to combine in the same acquisition a report for both tubes or multiple tubes. From Beckman Coulter website, you can download clear latency templates for QC control cells and data analysis and reports for Calusa-C. Calusa-C is available under a single license or network licenses and can be installed on offline computers dedicated to flow cytometry data analysis. It's part of the validated clear latency system workflow.
So let's start Calusa-C. In the QC report activity, we'll see here, I have already some data. So I will go to my folder and we have already acquired control cells. So let's go for the abnormal. So it's the abnormal empty tube. So let's put a second file here. Okay, so what about the data? Just go to this report sheet and normally you see here all the expected values, and if we are out of range, normally the lower and upper limit values will appear in red. So for the quality control, I replay only the M2 tube, and the abnormal data. So let's go now to data analysis. So remember, to simplify all the process of the ClearLab 10C, we provide all the templates for the QC, but also for the patients, for the data. So let's go now to analysis activity and open the protocol. So the protocol is we can take the M1 tube. The last version is the version 7 right now, available in the Beckman Coulter website. And let's replay data. So remember, we provide also a casebook with multiple cases. And in this casebook, we provide also the raw data. So first, I will use probably the M1 tube here, and we provide normal samples, so bone marrow, lymph nodes, and well blood. So here I will use the bone marrow ones. So we see the data again, verify that the gating is still approximately good, so no problem here. One of the function in Calusa is if you click right and you see here the resolution, if you have too many events, you can still increase the resolution to reduce a little bit the display and to better see the different cluster of cells. So this is the case here. So let's go back to this region here. So no problem for the gating. Seems to be nice. So it's a normal bone marrow. And we see here the expression of the different type of cells with the CD7 for some cells. We have the 64 for the monocytes. Normally there is no CD34 cells. And what's nice here, I can show you also a good option on the system. So for example, let me just create a new region. So I will create here just a region. So I just click right, you see this radial menu. I select, why not, just the rectangular region. I will select these populations here, okay? So all the cells who are CD34 positive. So if I click right and I click here, I can change the color. This is the first point, but I can also ask to show as rare event. So remember one thing is the DxFLEX can acquire up to 24 million events per data file. So it means that you can really collect a high number of cells. And if you are visualizing low density of cells, it's easy in Calusa just by selecting this option. So just click right, go to the display. And here, if you checkbox the show as rare events, the system will change the resolution of these specific dot cells and will highlight them in all the graphics. So you can see here where these cells are appearing. I'm not really surprised because it's a CD34 positive. So you see they are dim in CD45. So probably it's hematopoietic stem cells. So now the question is it normal or abnormal cells? I believe that these ones are normal because we are in a normal bone marrow. So you see very well where these cells are fitting. So you can still change the resolution of that by just clicking right, go back here, and you see that you have here a smoothing factor. So you can, if you have really a poor number of cells, you can increase the size of the dots. So if you are in a minimum, you can still see them very well. If you have few cells, you can still increase this resolution. So it's a nice tool to visualize quickly where the cells fits in all the other graphics. So CD34, very nice, and you see also where they are fitting for the other markers. So this is a very nice option. So this one is the template for the data analysis provided in the Beckman Coulter website. If you go to the report sheet, you can still see the different sheets dedicated for the reporting. You can also, remember, through Kaluza, send all the data to the alias if it's needed. Here, you see the different subpopulations of the leukocytes, including the granulocytic populations, lymphocytes, monocytes, and the dim expression of CD45 cells. You see here, after that, some other populations, mainly based on the CD34 expression, also CD64 and CD7. And after that, we go more in details. For example, in the lymphocyte subpopulations, we are looking for the sub-expression of the CD11b, 7, 34, 10, etc., etc. So we have multiple sheets here dedicated for different lineage. So here we are in the sheet for the monocytic lineages, where we see the co-expression of the markers for the monocytes. We have also for the granulocytes here, the subpopulations of granulocytes. We have also the CD45 dim, so where normally fits all these immature cells. So here, these are the reports. So let's now analyze another patient. We have here in the case book, we provide the case number 7. Let's just replay one data, is the first tube, the M1 tube. So I will put it down here. It will open without any protocol, and I will drag this protocol down to the sample. So just move and drag it down, and I change the protocol from the first tube to the second tube. So I can switch also, this one is nice. Here it's a density plot. So if I click right on this plot, I can go here and reselect, for example, to use the gating color. So it's nice because you remember I put in green the monocytes, in blue the granulocytes, in red the lymphocytes, and here usually in purple the immature cells. So let's put out this display of rarevans. Okay, and probably let me erase my region. Okay, so what we see here, we see a high proportion of monocytes, around 43%. So we have much more monocytes than expected. And we see also an immature population, a population with CD45 dim. And if we look for this population is CD34, has expression on HLA-DR. Is also dim in CD10, so it's abnormal expression also on these populations. It's also CD13 a little bit positive. Okay, so here this sample is identified as AML, so acute myelomonocytic leukemia. So we have the second tube, but we have no time for that. So it's just to show you the quality of the data. And if you are looking for, again, population who is not expressed too much, for example, I will take this one here. You can, again, select it, click right, choose the color to see it properly, and just display as a rare event show. So you see where these cells are fitting inside the space of the different markers and clusters.
Thank you very much for attending this webinar. It's part of 3 sessions of our leukemia and lymphoma webinar series. We hope you enjoyed the program today and you are listening in again.
Thank you both for your time today. We would also like to thank LabRoots and our sponsor Beckman Coulter Life Sciences for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions submitted during the live or on-demand period will be addressed via the contact information you provided at the time of registration. This webinar is part of a 3-part series, and you can find details for the previous 2 parts under the resources component on your screen. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.